Hello friends, this is Durga again from IT Varsity, and at this time I am actually talking about loading data effectively into the database. As part of that, so far I have covered how we can actually improve the performance by just moving data onto the database server and using tools like SQL Loader to load data into the database. The advantage will be there will not be too much network turnaround between the remote server and your PC if you move the data to the server itself. But when we run locally, it took around 30 seconds for one file to load because we have done it in serial fashion, and at times it might not be good enough. We might want to, so as we have 6 files, it will take at least 3 minutes to load this data, and again, depending upon the volume of the data, the time increases. So it will be better to do the parallelism, and for that your server should have enough process so that you can actually achieve true parallelism. So the servers which I am using have only 2 CPUs on each of the node, but still we will be able to get the parallelism, but not in the true sense. I will try to run multiple SQL Loader scripts parallelly, 6 at a time, and see what type of wait events we will get when the scripts are running in parallel, and we will see how we can tune the performance. So before getting into the details, I would like to show the scripts .sh and .ctl scripts which will be used to invoke SQL Loader for the file for a given file. So this script is invoking a CTL file or control file for SQL Loader, which will have the SQL Loader code snippet for year 2009, and it will be committed. It will be committing 10,000 rows at a time. I will increase it to 100,000. Okay, for that I am changing Perl P minus I minus E. Yes, 10,000 to 100,000, and then I want to use, I have to use G here, and then .sh. Okay, now if you look at, it's 100,000 in each of the script. Okay, now let's view CTL scripts. It is same, so it will have the location of the file. It is in the local directory itself, and it will try to load data into these 7 columns in the table in parallel. So before running this script, let me truncate the table on the target database which we want to load. This is a table called stock underscore EOD. So I'm using, I'm connecting back to the database, and also I have to add one more thing. I have to add the username and password so that I can actually run these scripts in parallel using NoHub. So yes, 100,000. I want to change it to 100,000 and then space, and then user ID equal to ptuning / ptuning sh. Okay, so I have to paste it in each of them. Okay, let me. So I have modified all the files by adding this user ID so that it will not prompt for the username and password. Once that is done, I will use NoHub and nysc underscore 2009.sh and ampersand and hit enter. Okay, there is some issue. Okay, I need to truncate the table because it has the data, it failed. Okay, now I'm truncating the table. Okay, now let me run this command. Now it is running. Now I have to run for the rest of the years also. 10. I'm not sure why it is complaining about permissions. Okay, I have to do +X. Okay, now it will run. 10 is done, and now 11, and now 12, and now 13. So if we have enough CPUs, this should be completed within 3 minutes, within 30 seconds, as everything will be running in parallel. So the same table is being populated with different data sets in parallel. So ideally it should be completed around in 30 seconds. Now let us see from the OEM how the performance looks like. You can click on this top activity icon and see what is going on. We need to see the details here. So you can see a lot of activities going on, and this is the query, I think, which is this is the query which is running, and you can click on that and it will take you to this window, and you can see that 6 threads are running at this time, and you can, what happened? So you can see this dangerous colors like this one, and you can click on that to see what the actual issue is. There is something called NQHW contention. We can see what is that waiting event, NQHW contention. And this is actually related to high water mark, because we are trying to load a lot of data at the same time, and table have to extend when the table is being loaded, and that's why you will see this wait event. And also there are other wait events as well for this query. We will see what are all those wait events in a minute. And the script is still running. It's not yet completed. It's beyond 30 seconds. And we can see if there is anything. The two files are loaded, and we will see how long it will take completely. You can click on this and see all the wait events you might be getting. So you got NQHW contention, NQFB contention, and more importantly, you get something called NQTX contention. So we need to understand why it is happening, and then we need to understand how this issue can be resolved. The reason why I am trying to reproduce this issue and trying to explain it is I have seen in many shops where people lack some basic knowledge and try to load the data in parallel, and most of the times data will not be loaded in parallel. Instead, it actually serializes the process because of this wait event called NQTX contention. And I will let it finish, then I will explain about this in detail. and I will also explain how it can be resolved. So this HW contention, and I'm not sure about FB contention, these might pop up irrespective of what you do. The reason could be because it has to allocate more and more storage to the table in parallel, and it can cause these extensions like HW, which stands for high water mark, I guess, and I'm not sure about FB contention. Yeah, this is also related to the extension of the table's storage to the table to accommodate this new data. Okay, so let us do the whiteboarding and see why this issue is coming up, and then we will try to resolve this issue and demonstrate to check whether the performance is really improved or not. So to understand about this TX contention, we need to go back and understand how data is actually stored in the on the file system for the given table. So in our case, we are using something called stock underscore EOD table, and for that table, what will happen is the data will be formatted in the form of blocks, and those blocks will be there on database files. You don't need to worry too much about those things, but what you need to do is, for example, if you take one of the blocks, this block not only have the data, but also it will have the block header. Okay, and that block header have something called some slots for storing the transaction related information. So what will happen is, by default, that there will be only one slot to store the transaction related information. And when I say transaction related information, you need to understand the DML concepts of Oracle, and you might be familiar that DML means insert, update, and delete. Okay, so whenever you try to insert or update or delete data into the table, the IO will happen at the least at the block level. So even though you update one record or insert one record or even selected data for one record, the entire block will be read from the file system into the memory of the server. So let's say this is the database server, and this is memory in the server, and IO happens, and each block will be read into the memory. But when it comes to for select, it is enough to just read the data into the memory and do processing on top of that. But when it comes to insert or update or delete, we need to know whether there is any transaction happening on that block for several reasons. I don't want to get into too many details here, but just remember that whenever IO happens for insert or update or delete, even insert or update or delete, it has to read blocks into the memory, and then it has to insert data into those blocks and reapply onto the database files so that it has the new data or delete the existing ones from the block. As part of that, for each and every transaction, for each and every insert statement, for any of the records in the table, in that block, for example, let's say this table called stock underscore EOD have 100 blocks, and it has 1 million records. So each block will have 10 records. So even if it is trying to update one record or delete one record or insert one record into that block, still it's a transaction at the block level. Sorry, it's an IO at the block level. So it has to update the slot saying that transaction T1 is trying to update or insert or delete a record in this block, even if it is just one record. Similarly, if transaction try to update 100 records and one of the record falls under each of the block, then the slot will be filled that T1 transaction T1 is trying to update few records in this block. It will not tell which records, but it will just make a marker saying that transaction T1 is trying to insert or update or delete record into these blocks. So once you have that lock, until the transaction is committed or rolled back, that slot will not be cleared. And unless it can be cleared, no other transaction can get hold of that block and start doing the transactions on that block, like insert, update, or delete. So when it comes to the slots, it's a configurable parameter, and if you go back to go back to the database and run this query called select star from dba_tables, where table name equal to stock underscore EOD and owner equal to p tuning, and when you run this query, you can see that as part of the metadata for this table in this DBA tables view, there is a parameter called ini_trans. So this is the parameter which will control the number of slots for each of the block associated with the table. By default, for a given table, it's 1, and also we have the primary key for this table. So let us see select star from DBA constraints, where table name equal to stock underscore EOD and owner is p tuning, and run this query. And this is the constraint name because it's a system generated name, as we did not give the constraint name here. So select star from dba_indexes. So each and every primary key constraint will have index associated with it, and we can actually I can search on the table name itself. I don't need to give the index name. Okay, and you can run the query, and you can see that there is an index associated with it, and this one also have the parameter called ini_trans, and it has 2. So even the index also will be stored in the form of blocks. If you want to understand how the data is stored, you can go back to the previous video in my performance tuning playlist, and it has a video called file operations, and it explains how the table data is laid out on the file system in detail, and even for indexes, the data will be stored in the similar fashion as I have explained earlier in this picture. It also will be stored in the form of blocks, and also that block will have the header, and it has slots for the transactions, and the number of transactions are the configured value for ini_trans for index is 2 by default. So at any point in time when it comes to index, only 2 transactions can work on a given block simultaneously to insert or update or delete the data, whereas when it comes to table, only 1 transaction can insert or update or delete in a given block of the data. As long as if you are running parallel DML, and if it is going to different blocks, then there is no issue. If both the DML commands are trying to update same block or insert data into the same block or delete the data from the same block, then there will be contention called NQTX contention. And to address that issue, what we need to do is, there are 2 ways to address this issue. One, we are trying to commit every 100,000 records at a time. Okay, so you can decrease that value to more manageable number that will perform the transactions more quickly. If we reduce from 100,000 to, let's say, 1,000, now you are trying to finish off transaction every 1,000 records, in parallel. So automatically the contention will go down. It will not go away completely, but it will go down for sure. That is one way to address this issue, but the side effect of that is there could be issue of too much committing on the database, again, which is a very expensive operation. So you can do that if you are trying to uh, load smaller set of data, and if you don't mind too much committing happening on the database. That is one approach. And second approach, to modify the table by increasing the initrans. So we'll try to demonstrate the second approach first, where we actually modify the initrans. So for that, let me truncate the table. I will not be or let me drop the table completely if the data load is done. So let me verify. Probably it would have done by now. Yeah, it is done, and it took almost 12:24 to actually it took more time than probably it might take by doing it serially, or it could be the same time if we do it serially. The reason is the process have become serialized because of this NQTX transaction, as we are trying to commit 100,000 records at a time. Let me truncate this table first. Okay, table is truncated, and now let me reduce the commit rate, and then we'll come back and modify the table structure, modify the initrans to a higher value for both table and index, and we will see the performance of that also. So for that, what I am trying to do is I just so instead of 100,000, I will change it to 100 and hit enter. Now I will run the no-hub commands again. And hit enter. So now we are trying to commit every 100 records in parallel, and you might not see this NQTX contention as much as we have seen earlier, but it can lead into some other wait events that are primarily related to commit, because it has to do lot of IO as part of the commit, and it's a very expensive operation. Let's see how it goes. While the query is running, you can actually validate how much data is being loaded into table by just running this select count of 1 from stock underscore EOD query. So already 866,000 records are loaded. Total we have 3 million records. So this is much faster, I guess, compared to the previous run. Let's see how long it will take. So now you can see that there could be different wait events. Let me click on this query and see what are the wait events we are getting now. So we still have NQTX contention, but it need not be as much as it used to be for 100,000 records. Okay, we will validate that by actually checking how long it took. But you can see that there are other wait events like log file sync and data file init write, db file single write, etc. So even though we are able to load a lot more data in simultaneously in using multiple threads, the servers are not powerful enough to load data in parallel, because we have only two two CPUs on this on each of the node in our rack database, which we are trying to demonstrate this. Okay, last time it took almost 12:26 to 12:34, almost 8 minutes, and let's see how long it will take now. So even with single thread approach, it will take more than 5 to 6 minutes, because 2009 dataset is smaller. That's why when we run for 2009, it just took 30 to 40 seconds. But it will actually take more time for the rest of the data. So we can actually run this query to see how much it is done. So that, yeah, it is almost done. Yeah, almost 5 are done. There is only one more. So you can see the difference. Last time it took almost 12:26 to 12:35, which is 9 minutes, and now it started at probably 12:44, and it is already done in 2 minutes. Yeah, it is done. Okay, you can see the difference. So the last transaction started from here and ended here. You can ignore this blue part. It is just after the transactions are committed, there could be some write operations onto the files. You don't need to worry about it, but I can confirmly say that it is completed here, whereas it took almost 2.5 times more time than this latest run, where the commit rate is 100, because our transactions are smaller this time, committing 100 records at a time. So if your table have tens and thousands of blocks, then for 100 records, all the transactions trying to hold the same block, the probability is very low compared to when we are trying to commit 100,000 records at a time. So definitely having commit rate to a more manageable value can improve the performance, but if you reduce the commit rate to, let's say, 1, then the performance can be bad. And even if time is lesser, but still the database might not be in a healthy state. So you need to keep in mind, you should never use commit rates of 1 or 10, etc. You can start with 100 or 1000 at the least, and you can go to the value depending upon the initrans on the table. If you are trying to load lot of data at the same time, and if you want to use even 100,000 rows at a time, by increasing the initrans, you can actually improve the performance quite a bit. We will see the demonstration of initrans as part of the next video. And for now, I hope you understand how by reducing the commit rate we can achieve the good degree of parallelism to load the data using parallel threads pretty quickly compared to using the single thread. And irrespective of how you are achieving the parallelism, the concepts are same. You need to just focus on the commit rate and the initrans. By keeping these two things in mind, you can achieve very good parallel degree compared to having a very high commit rate or very low initrans values. That being said, I hope you are enjoying the content on my channel. If you like this video, please click on the like button. If you have any questions or if you want to provide feedback, please use the comment section of the video. And if you have not subscribed to my channel yet, please do so. You will get to see a lot more content like this over time. Thank you. Bye.